Hello, good afternoon, or technically still good morning, everyone. I'm Owen Wang, a current rising senior at Acton Boxford Regional High School. So I'm sure all of you guys have seen solar cells popping up in the US and around the world, and knowing how much the US likes to throw away things, I've always wondered how can we prevent these solar cells from ending up in the landfill and then detracting from their eco benefits that they had during their lifetime. So today I'm going to be presenting a new process that we discovered to reclaim the silicon in the solar cells at their end of life. So first, a little bit of background on the solar market. So currently we have a solar generation capacity of 700 gigawatts worldwide. And by 2050, this is predicted to rise to 4,500 gigawatts. So solar is clearly a currently growing form of electricity generation, but this generation is not completely homogeneous. There are multiple different types of panels on the market currently. Crystalline silicon panels are the most prevalent because they were the first technology to be developed. As we see in this chart here, in 2014, pretty much almost all of the solar panels on the market were crystalline silicon. And then we see as time goes on, thin film takes a little bit more market share, and then other technologies also grow as well. So since crystalline silicon was the first technology and is currently the most prevalent, it is also the one that first needs to be recycled, since they're now slowly reaching the end of their 20-year lifespan. But even crystalline silicon panels aren't all the same, as we discovered. There are multiple different types here, just two of them. Though there are different types, they do have similar contents, including silicon, aluminum, silver, and silver nitride. And to the left here, you see a PERC cell, and PERC is the first generation of crystalline silicon panels, and thus are the most prevalent, and currently is the type that we're investigating to recycle. Taking a shift towards solar panel waste, as we see the solar panel waste market is currently valued around 100 million, and it's predicted to grow to 500 million by 2027. As we see, China is the current largest producer of solar panel waste, with the US coming in at second, predicted to produce around 7.5 million tons of cumulative solar waste by 2050. But since new technologies are growing, it is very possible that some of the panels may be replaced prematurely. And thus, if we look at the early loss scenario, we could be looking towards more closer to 10 million tons of cumulative solar waste by 2050. Either way, it's predicted that we will have 78 million tons of solar panel waste globally by 2050. The majority of the value in this solar panel waste is in the silicon and silver, and then second is aluminum. One of the major problems with throwing this waste just in the landfill is that these panels contain heavy chemicals, heavy metals like lead and tin, due to their soldering processes, among other chemicals that are harmful to the environment. So this is what the current recycling approach in Europe looks like. To the right is the thin film recycling process, so I won't be going into that detail to that currently, but if you look to the left, that is their process for crystalline silicon panels. So it first starts with a disassembly process, and then a thermal treatment, and then an etching step. There are a few disadvantages to their current workflow right now, including their use of toxic chemicals like hydrofluoric acid in their etching process. In addition, since they're thermally processing at 500 C, this is also a pretty energy-intensive process. And finally, they have, as you see, they have only 85% of silicon reuse, which is a very good number already, but we would like to see that a little bit higher as well. Finally, one major problem with the etching process, apart from its use of toxic chemicals, is that it is very not universal. because the etching has to be very carefully timed so that they don't remove extra material or don't remove too little material. And due to the variation in solar panel types and the variation among manufacturers, that becomes a very cumbersome process, especially if you have mixed waste streams. Looking towards the US's process, the US primarily only recycles the glass, the aluminum frame, and the junction box. And the rest, as you see here, is just sold as low purity silicon and a metal mixture. And so this means that their material is low purity and has a very low recovery rate. And then the value is also lost in this as well. So what can we do? What does a better solution look like? So this is what our recycling process looks like. We aim for over 90% recycling rate, as well as not using any harmful chemicals like hydrofluoric acid. In our recycling process, we also generate clean hydrogen as a byproduct, and we are able to recover the silicon and silver at high purities. And then these could both be used in potential other applications like lithium-ion batteries, or the high purity silica could be used as feedstock for silicon for higher purity silicon applications like semiconductors and solar panels. Finally, our process is universal for all crystalline silicon panels, so it doesn't matter what type it is, our method should work for them. We've completed this process both at lab scales and 100-gram scaled up runs. So looking a little bit closer, this is former process. This is not what we're building on, but as you see, the aluminum frames are disassembled, and then the glass, copper wires, and then EVA polymers can be removed, and then we receive a solar panel, silicon-based solar cell powder. And then our first step is to leach and filter. So we use a sodium hydroxide solution to leach, to pull pretty much everything in the solar cell powder except for the silver, which can then be filtered off. And then through this process, we also generate hydrogen as a byproduct. Now, once we filter out the silver, we can then take the resulting solution, the resulting silica solution, and then precipitate it with an acid solution. And then through decreasing the pH of the silica solution, we are able to precipitate out the silica and then retain everything else in the wastewater mixture. And this wastewater mixture contains low amounts of aluminum, lead, tin, and some other elements. But it is at a low enough amount that we believe that it shouldn't be that much more work to either extract these elements or to process this wastewater for disposal. So to take a look at what solar panels look like from the industry, this is a set of pre-production solar panels, so they haven't yet been soldered together. And pictures A, B, C, and D are of the top, and then the bottom row, E, F, G are of the bottom. So if we take a look at figure B, there are two areas. There's a lighter gray area and then a darker gray area. If we first look at the darker gray area, figure C is a close-up image of that with its EDS mapping. And we see that it is primarily silicon nitride. And the lighter parts, shown in figure D, are primarily silver. And then the reverse, the bottom, is primarily aluminum. And this is very typical of a PERC cell, as we see here. In this diagram, we have a silicon nitride outer anti-reflection layer and then an aluminum rear contact. So once we receive this, then this can be ground up into our pre-treatment powder. And then both XRD and ICP show that this is primarily silicon with aluminum as our major impurity, and then a little bit of silver as well. One thing to note is that we do see very low levels of lead and copper in this, which is because these are pre-production panels and they haven't yet been soldered together. So these levels are a bit lower than what we would expect in post-use spent solar cells. Now with this process, we can begin the leaching process. And our goal here is to recover the silicon and the silver. And we manipulated the following constraints to increase our leaching efficiency, including concentration, the temperature, the concentration of the sodium hydroxide, the temperature of the leaching, the excess amount of sodium hydroxide, as well as the leaching time. So if we take a look at our graphs here, concentration, we settled on 10 weight% of sodium hydroxide, which gives us our optimal leaching efficiency. We settled on 50 degrees C for the temperature. We saw a positive correlation between temperature and leaching efficiency, but factoring in the amount of energy it takes to heat up our solution, we decided that 50 degrees C would be the optimal condition. And then we investigated the amount of sodium hydroxide to silicon mole ratio. The equation, the reaction in theory uses 2 moles of sodium hydroxide for every mole of silicon, but we experimented on how much excess we need for the optimal reaction, and we determined that around 2.2 moles of sodium hydroxide for every mole of silicon is the optimal. Finally, with leaching time, we didn't see any major difference above 1 hour, so we just kept it at 1 hour. Overall, all these 4 constraints optimized together, we received a leaching efficiency of around 93.68%. With this silica solution, we then added hydrochloric acid to precipitate out the silica. Sorry, one step before that. So as I mentioned earlier, we would filter out the silver, which does not go into solution. And taking a look at the filter cake, we see that it's primarily silver, aluminum, and silicon on our filter paper. The silver can be taken and further purified. Unfortunately, the silicon does get chemically bonded to the aluminum as a hydroxy sodalite, and this silver is not really easily recoverable, so this would just be a loss in this process. So now we can take our silica solution and add acid to it to precipitate out the silica, and we get the silicon dioxide. It is a nano-sized silicon dioxide particles, and they're amorphous, as shown through this XRD. And we are able to extract around 99% of the silicon dioxide out of the silica solution through our precipitation process. Taking a closer look at its purity, you see we have EDS mappings as well as ICP results, and pretty much no impurities were detected through SCM, while very low impurities were detected through ICP. As we see, ICP shows that our primary contaminants are sodium and aluminum. We predict that the sodium wouldn't be very hard to remove just with further optimized washing steps. And then the aluminum would, to remove the aluminum, we would have to refine our precipitation process a little bit more. But overall, we already have a 99.994% pure silicon dioxide here. Just a brief materials cost analysis. This is numbers for 1 ton of post-production solar panels. And we would expect to recover around $938 of materials, the value of materials from 1 ton of post-production solar panels, while only spending $55 in terms of chemicals. Obviously, this is only a materials cost analysis. This does not include any capital that may be needed, but this shows that this could be a very profitable process. So in summary, we were able to extract around 92.77% of the silicon from our solar panels. And then with a resulting 99.994% pure silicon oxide, we were able to extract the silver from the panels as well. Unfortunately, since we only did this at lab scale, we weren't really able to extract enough to be able to further characterize or purify it. But in theory, the silver would be able to be recycled. In addition, during our leaching process, we were able to generate hydrogen as a byproduct, which can then be used in other applications like fuel cells, etc. And finally, this method has a high potential for profitability and commercialization. This project wouldn't be possible with the help of a few mentors, Dr. Xiaotu Ma, Jiahui Hou, and Zexin Wang, and then everyone else at the Electrochemical Energy Lab at WPI. Thank you very much.
Thank you so much. That was really interesting. So we have time for questions. Again, I'll start. So it's great you did this analysis of like the chemical purity and the materials and the costs.
Yeah.
Did you try to do like an analysis of the energy spent? I mean, I don't know. I'm pretty ignorant. So how much of this needs heat, transport, other just costs that maybe not too hard to obtain, including the analysis.
In terms of the heat, the only heat that we added was during the leaching process. Everything else was just at room temperature generally. In terms of the transportation costs, I'm not so sure about that. We didn't really investigate into that. I could foresee, costs in terms of like separating the different types of solar panels, but since this process is universal, in theory, that wouldn't be really required because we could use a mixed stream of various different types of crystalline panels.
So they need to be like conveyed in and broken up or something, right?
Right. Oh, okay. Yeah. In terms of that, we don't, because the broken up, the disassembly process was not in the scope of our projects. That would be, pre-existing methods that would be used. So we didn't really look into that part. But yes, that would be a cost that we would have to consider as part of the process. Yeah.
Could this be attached to a regular kind of recycling operation? Or does it need to be like in some special location or?
Because of how solar panels are constructed, they are constructed in a way that is very hard to disassemble to prolong their life, right? So it would be difficult to integrate them directly in other recycling processes for other materials. So they would likely have to be processed separately from other recycling.
Great. Any questions from the audience? One more, again, was just asking, can you sort of get the idea of the yield of hydrogen
Yeah.
from per, pound of panel or something?
So we were only able to theoretically calculate it. We didn't really have a good, we did use a balloon to try to capture some of the hydrogen, and we were able to confirm that it was hydrogen. But we didn't really have a safe enough way to quantify how much would be produced apart from theoretical calculations.
Okay.
Yeah.
Thanks so much. Very interesting.
Thank you very much.
Okay, and our next and final speaker is Zhilong Zhao. I believe. There he is. And again,